All right, of the lessons in this unit, this one is the most important. Periodic trends will help us to understand why elements behave the way they do and how they bond, how they are named, and how they react. And so we're going to come back to this information as we move forward in the rest of the units. So this is the most critical to understand. And periodic trends start with effective nuclear charge. Because in an atom, electrons experience two types of forces. The first force is an attraction to the positively charged nucleus. Remember, opposite charges attract. So electrons are attracted by the nucleus. And the nucleus is, in its positive charge, is what holds them in orbit and keeps them from flinging off into space. However, they also experience repulsion. They don't like each other. That'll become a big thing when we get into covalent nomenclature and molecule shapes. They don't like each other. They want to get as far away from each other as possible. And so that also plays a key role. So each level of electrons partially shields the outer electrons. So if you have 3 energy levels, the first 2 kind of get in the way and repel the outer group a little bit. And that third level just cannot expel the full pull of the nucleus. Kind of also makes sense that, like if I've got an electron orbiting here, it's closer in, and it's going to feel more of that pull than if I got an electron way out here. All right? And so these out here feel less pull out here, and we call that the effective nuclear charge, or how much of the nucleus are they feeling? How much of that charge are they feeling? And it is given the symbol ZEFF. I don't know why, but that is the symbol that is given for effective nuclear charge. So with all of these trends, we need to know how they work on the periodic table. And the way I do this, and different books do this different ways, but the way I do this, just to avoid confusion, is I always draw my arrows in the direction in which something will increase. Okay? So when we go down, it decreases. So like when I'm in hydrogen, that electron's right next to that proton. It's going to feel it perfectly. But when I get down here to francium has I can't remember its atomic number off the top of my head, but it's got like 70 something other electrons in between this electron and the nucleus. And so it just has a hard time feeling that nucleus. And so this has the lowest effective nuclear charge down here, francium. And that'll come into play as we go along later. And then as we go across, that effective nuclear charge is going to increase because, remember we said it's kind of like adding layers on a house, that, this group here, they're all on the second level. They've got one group inside of them, or a third group here. Let's look at the third period. So they all have 2 levels in between them and the nucleus. But, so sodium does and chlorine does. But chlorine's going to feel more of the nucleus because there's more protons there to feel by the time you get to chlorine. If you go from 11 protons to 17 protons, and it makes a difference. All right. Atomic radius. This is not an exact measurement. Kind of as we've dealt with already in quantum, electrons aren't exactly certain where they are. So it is dependent on electrons, not related to the mass in any way. It's all about electrons. So heavier atoms are not necessarily bigger. So it's usually measured as half the distance between 2 adjacent atoms. That's kind of how they can figure out where the nuclei are pretty well. So this is the opposite of effective nuclear charge, because the way this works, the more the effective nuclear charge is, the better it can pull in those electrons. Because remember, they're being attracted. Electrons in the nucleus are being attracted. So the stronger the effective nuclear charge, the smaller the atom. So atomic radius works exact opposite. Instead of going up and to the right, it goes down and to the left. So francium's the largest atom out there. Helium is the smallest. Once again, we can look at group 3. If you have a periodic table with you, that would be helpful. So atom number 11 is sodium. Atom number 17 is chlorine. Once again, they have the same number of energy levels. They're both on the third period. But because chlorine has, 17 protons, and it's got a stronger effective nuclear force there than sodium, and it's 11 protons. Chlorine is half the size. So it is half the size of sodium. And that's kind of where that's coming from. Going down, it makes a little more sense. If you add energy levels, it's like adding floors on a house. The house is going to get bigger. Francium has, however many protons and electrons on it. It can be a lot bigger than hydrogen with its 1. Okay, so francium's the largest, helium's the smallest. All right, ionic radius works the exact same way, except we're going to make a distinction between positive and negative. And so the key thing you need to know here is that it works the same way as an atomic radius, but you need to know that negative ions gain electrons, that extra electrons repel each other, making the ion get bigger. So, and then positive ions get smaller because they give away that electron. That effective nuclear charge stays the same, but you got fewer electrons now, so it pulls it in tighter. And in fact, where we talked earlier, where I said like sodium is twice the size of chlorine, when you form their ions, it actually flips. The chloride ion gets bigger, and it actually ends up being twice the size of the sodium ion because it gets smaller. And so it's a pretty dramatic shift. I will never ask you, and I don't think you should ask your students, to ever compare a negative ion to a positive ion, because you just can't do it unless you have a chart. But you can compare positive ions to positive ions. You can compare a hydrogen ion to a barium ion. You can do something like that. You can compare fluorine to carbon. You can do something like that. All right. Before we move on into the rest of the trends, we need to discuss valence electrons. So this is pronounced valence, not valence. So valence electrons are the outer layer of electrons, and they are equal to the number of s and p electrons. So as we go across the representative elements, the easy way to do it is just simply look at the group number, and it gives you the number of valence electrons. Group 1 and 2 have 1 and 2. And then group 13 through 18, you just take the 1 off the front. So group 18, take the 1 off front, gives you 8. Group 16, take the 1 off the front, gives you 6. And that's how you do figure out valence electrons. Transition metals are generally considered to have 2 because of the s2 electrons, but the d electrons can get involved and it gets wacky. So for the most part, we're going to say it's s and p electrons, and we're going to use this little table here, or use that pattern to figure out what your valence electrons are. These are important because of what is known as the Octet Rule. Okay, the Octet Rule states that atoms want to have 8 valence electrons. All right, when we're dealing with positive and negatives, I like to sometimes just simplify it and say they want 0 or 8. The idea is if they go to 0, the shell underneath them is actually full, and they get to 8. So like, for example, sodium is 3s1. It gives away that 1 electron. It's now going to have 2s2 and 2p6 full. It's going to have 8 valence electrons. But for the sake of simplicity, I call it 0 or 8 just to make things a little bit simpler. So atoms with less than 4 valence electrons prefer to lose electrons. I mean, think about it. If I gave you a game and I handed out each of you random number of cards between 0 and 8, and I said, hey, you need to trade cards until you get to 0 or 8 and then you'll win. If you started with 2 cards, you can either give away 2 cards to get to 0, or you can try to gain 6 more cards to get to 8. Which way are you going to go? I mean, it's pretty obvious that you would want to go this way. And then nitrogen, which has 5, is going to go this way to get to 8, because it's easier to gain 3 than it is to lose 5. And so that's kind of how the Octet Rule works. And that's going to be important as we look at these next 2 periodic trends. The next periodic trend is what we call ionization energy. So ionization energy is the energy required to remove a valence electron from an atom. So it is a measure of how tightly an atom is holding onto an electron. So let's back up for a second. So it's the energy required to remove something. It's the energy required to do something. So if someone comes up to you and says, hey, I want you, your boss comes up to you and says, hey, I want you to completely and totally organize the chemistry stockroom this summer. We're not going to pay you, anything extra. Just you're expected to come in and clean the stockroom. How much energy is it going to require to make you do that? Probably a good bit. A lot of willpower and a lot of energy to get up and do something just because it's difficult, it's onerous, you're not being compensated. Now let's take that again and said, what if somebody came up to you and said, hey, I'm going to give you this $100 gift card to this really fancy restaurant. The only catch is you have to use it tonight. How much energy is it going to take to make you go spend that coupon tonight, that gift card? Not a whole lot. And so we think of it the same way. So if an atom really wants to give up an electron, then we would say it has a low ionization energy. Because it's not going to take much energy to make it give it away, because it already wants to give it away. As opposed to somebody on the other end of the spectrum who wants to gain electrons, who doesn't want to give them away. It would take a lot of energy to pull them away. So that's what we have here. So looking at our same example of calcium and nitrogen, because calcium wants to give away electrons, it wants to go this way, it's going to have a low ionization energy. In contrast, nitrogen, because it's over here and really wants to go this way, it doesn't want to go to the left, it wants to go to the right. And giving away an electron would make it go to the left. And it's like, no, I'm almost there, you can't make me. And it's going to fight you tooth and nail for that electron. And so it's going to have a much higher ionization energy because it's going to fight losing that electron. It's like, no, I already have 5. I only have to get to 8. Now, atoms aren't really personified like this. They aren't really thinking this, but this is how it behaves. So the trend itself works this way. So we say it increases going up and right, and it has to do with the effective nuclear charge and so on. The way it works going down and why, so for example, fluorine holds on tighter than bromine. And part of the reason being it's easier to pull off something that's bigger because that electron is so much further away from the nucleus. It's easier to steal. So the way I think of this with my students is if I have I draw a small chicken yard and then I draw a really big chicken yard and I put a farmer with a gun in the middle. And I'm like, hey, you're a fox and you got to steal chickens. Which one are you going to steal chickens from? The small chicken yard or the big one? And the kids generally get it's like, hey, I'm going to steal from the big one because I can get the edge and stay away from that farmer with the gun. Well, same thing. If something's going to try to come and steal that electron off of either bromine or fluorine, it's easier to steal it off of bromine because bromine is so much bigger and that electron is so much further out and it's easier to snatch. And so that's part of why this decrease is going down, meaning once again, my arrows are always drawn in the direction it increases. So it's a lot harder to pull off from the smaller one, so that increase is going up. All right. So atoms can have second and third ones. For example, calcium wants to lose 2 electrons to get to 0. So it would have that first one, and then it would have the second one. The second one's always going to be higher than the first one. Well, for the most part. There are some little exceptions having to do with some rules in quantum mechanics that we did not learn and are not going to go into because they're more of an AP Chem or a college Chem topic. All right. Next trend is called electron affinity. So electron affinity tells us how easily an atom wants to accept an electron. This is essentially the opposite of ionization energy. That instead of removing electrons, we're adding electrons. So atoms that want to form negative ions, are going to have high affinity. Because the word affinity means a like for something. You have an affinity for something. How much do they have an affinity for electrons? Atoms that want to form positive ions, they have low affinity because they don't want the electrons. They'd rather lose them. They don't want to gain them. And then noble gases are said to have, an affinity just barely above 0, meaning they don't really care. All right. So when we look at the trend, though, the trend goes in the exact same direction as ionization energy. But didn't I just say this was the opposite thing? Well, it is. But it's also measured in the opposite way. So if I take the opposite thing and I measure it in the opposite way, the trend goes the same direction. odd, but that's how it works. Because we're not talking about how much energy it's going to take to add the electron. We're just saying how much they want you to add it. And these guys over here, they want that electron. And so they're like, hey, give it to me. I got high affinity. I will gladly take that electron. Get to 8 and party. Okay? And that's kind of how they act. So, electronegativity. This one is not so much, it has a trend to it, but it's something you're always going to get from a table. So this is the ability of an atom to attract electrons in a bond. Okay, so we're going to learn about covalent bonding in the next unit. And in covalent bonding, the electrons are shared. But if you had siblings growing up, how hard was it for y'all to share perfectly, 50-50? Like it almost never happened. Okay. And so this measures how much the sharing is not equal. So it's given a number between 0 and 4. Here's a table. Fluorine has the highest electronegativity of 4. This one stops down at cesium at 0.7. They don't even do francium in groups period 7 down here. And so they do it that way. So when we look at this, we have to compare the numbers to each other in a bond to see what's going on. Okay, so for example, if we had nitrogen and chlorine with each other, they would both have electronegativities of 3. That's no difference. They're going to share perfectly, 50-50. Okay, we look at water, oxygen and hydrogen, 3.5 and 2.3. They have a difference of about 1.2. We call that uneven sharing, that the electrons are going to be a little bit more over here on this side with the oxygen and a little less with the hydrogen. And then magnesium and oxygen, that is so different, like it's a big difference of 2.3, that they're not even sharing anymore. The oxygen just literally takes the electrons away, and we call that an ionic bond. We'll deal with that later. But the trend still works just like ionization energy and electron affinity, that it increases up and to the right. You'll always be given a table with these. All right, overview. Up and to the right, effective nuclear charge. And to me, this is the easiest way to remember this. You can go back and focus on the why. I think the why is important to know. But at the end of the day, this is all you need to know. So, end of the day, ionization energy, electron affinity, electronegativity, and effective nuclear charge increase going up and to the right. And when I test this, and you'll see this in the workbook, I always compare things where it's obvious which way it goes. Like I'm not going to compare bromine with carbon, because carbon's up, but bromine's more to the right. Which one is it? And you wouldn't really be able to know unless you looked up the values. And so I like to compare things that are either in the same group. I would compare fluorine to bromine, and fluorine would be higher. Or I would compare the same period, boron versus fluorine, and fluorine would be higher. Or I'll test this way. Okay, copper. Copper's about here versus fluorine's over here. Fluorine is both up and to the right, so it is definitely higher for effective nuclear charge, ionization energy, all 4 of those. The only ones that go down and left are the 2 size ones, atomic size and ionic size. And then just remember with ionic size, positive ions lose electrons, therefore they get smaller because they lost something. Negative ions gain electrons, therefore they get bigger. And that is the general gist of doing these. So if you have not yet taken the time to memorize your elements, their symbols, and their names, you need to do that before you move on into the next unit on covalent nomenclature. Because elements and their symbols are essentially the alphabet of chemistry. And if you don't know the alphabet, then you can't make words and sentences. Because nomenclature, how we name chemical compounds, are the words, and then when we start doing chemical reactions, those are the sentences. And we need to be able to know them and speak them fluently in order to progress and move on. So if you don't know your alphabet yet, if you don't know those chemical elements, their symbols, and their names, you've got to learn that. You've got to be able to go back and forth. If I give you the symbol, you need to know the name. If I give you the name, you need to know the symbol. It is essential for doing chemistry. And so make sure you have that down, and I will see you in the next unit on covalent nomenclature.